Once again. This is the price, for instance, for getting the transparencies sent to your office. Thank you.
Well, thank you for your attention. I'm actually excited today, not just because it's the last lecture, which is, I must admit, a reason to be excited. But I think I found a medium to say what I want to talk about. In fact, remember I told you I'd give you some subset of the final few topics? Well, I think I realized a way to mention all of them. And I've been trying to skirt in these lectures talking about everything and therefore saying nothing, and talking about one thing and really not giving you perspective of the field. And so I've tried to look at a few topics in some detail, from dark matter, and yesterday the age of the universe issue, and dark matter detection. And yet I did find the last few topics I did want to cover because they're interesting. But obviously I can't cover them all in detail. But so what I'd like to do with each of them is present what I think are the salient features, just some key overview ideas, but look at one or two things that I think are the most important things in each area. It was also mentioned to me that I might want to list some references, since I've been, as I told you, I studiously will avoid putting every reference on every paper and every transparency. And I also told you I'd studiously avoid referencing anyone here. But let me just indicate, of course I'm going to flash this and you can't copy it down now, but those of you who want to get the transparencies, what I did was put some books, because I'm not going to give every article, there are millions of them. But here are some reasonable books from which you can then begin to go through the literature. And by books I also include 2 physics reports that are recent and 2 that I'm supposed to be writing in various sorts that'll come out in the next while. So I take it off now, but it's there so you can get references. Okay, last time I initiated the topic of stellar evolution by talking about, in some detail, the issue of the age of globular clusters and how stellar evolution can affect our understanding of one of the most fundamental parameters in particle physics, which is the energy density of the universe, and presented for you the issue of the age problem and then the question of whether there is indeed an age problem. Now I want to talk about 3 other aspects relatively quickly having to do with stellar evolution. And I will, in spite of the predilection I told you yesterday, mention solar neutrinos. But I won't do that right away. The first thing I want to talk about is why stellar evolution itself provides such a significant handle on being able to constrain the parameters of elementary particles. And I want to present to you 2 interesting facts which, whether or not they're useful here, are always interesting things to know and talk about at cocktail parties. And I was going to question you and poll you by this, but some people know the answer to this, and if you know the answer to this, you're not allowed to say what the answer is. But you might want to guess how long it takes for a photon to random walk from the solar interior up to the surface. I feel I should put someone on the spot and ask them, but maybe I'm not allowed to. But think about that for a minute and guess what your naive best answer for that is. And then also guess the time it takes for the sun to radiate its stored thermal energy. Namely, if I turned off all the nuclear reactions in the sun right now, and the sun is hot, how long would it take to radiate away that heat? Those are 2 very interesting dynamical timescales, and they set the reason why elementary particle physics can affect the sun so much, even if the elementary particles are very weakly coupled. Well, let me give you the answers. I'm not going to put you on the spot. But it's kind of remarkable to me, at least the first time I thought of this. The photons random walk out of the stellar interior is one way of thinking about it. And of course, the random walk time depends upon the step size, which depends upon the photon mean free path, which depends in turn upon the Thomson cross-section. But you can calculate that. That works out to be 1 centimeter. And the time it takes, clearly, therefore, is 1 centimeter over c. And then you can ask for the escape time, and it's about 10,000 years. It's kind of remarkable that it takes a photon 10,000 years to escape from the sun. And that's very important. The other thing, which I actually gave you the answer to yesterday, so if you were listening, you would know the answer in a sense. And this was the calculation that Kelvin Helmholtz did that was wrong and deviated so much from the evolutionary age of the Earth. And that was that if they didn't know the sun actually produced energy, and they just said it's hot, and how long will it take to cool down, and you can calculate that, and you find out it's 10 to the 7th years. Gravitational settling time. And so that's the time it takes to actually radiate away all of its thermal energy. Now, the reason these two disagree is that most of the thermal energy in the sun isn't carried by photons, it's carried by the random motion of particles. But these are rather long times, which is what is important to realize. The sun will cool down in a long time, and a given photon takes a heck of a long time to get out of the sun. By the way, another thing this is useful for, I found that these things which are based on fundamental physics are always good to talk to creationists about. When people talk about the age of the universe and it being 2,000 or 5,000 years, you can point out that not a single photon would have gotten out of the sun in that time. In any case, the point is that therefore the sun is extremely sensitive to any extra energy loss mechanisms. Because anything which can take energy out instantaneously will dramatically affect the sun. And that's why we get strong constraints on weakly interacting particles. So what is the effect of adding a new weakly interacting particle that can take energy out of the sun immediately? Well, remember the fact that the sun is in hydrostatic equilibrium, and therefore the pressure is related to the gravitational force, and that's what's holding the sun together and stopping it from collapsing. So the effect of adding some extra energy loss mechanism, a cooling mechanism, is to reduce the pressure for the same energy generation, because the thing that keeps the pressure up is the fact that the photons are random walking. So if I add some new energy loss mechanism, I reduce the pressure for the same energy generation. Well, what will the effect of reducing the pressure be? It will make the star contract. But making the star contract will make it heat up. So the rather amusing thing is that by cooling the star, you heat it up. The effect of any extra cooling mechanism is to heat up the star. It perhaps is against your naive intuition, but once you think about it, you realize it's the only case. So essentially, in order to get the same pressure, the sun has to burn hotter. And so the effect of any extra cooling mechanism for a star that's dominated by its pressure is to heat it up, and that will therefore change the profile of the star, change its central density and its central temperature. And that's an interesting fact that I wanted to tell you about. And the more important thing then is that it burns faster. Adding a cooling mechanism will cause the star to burn up its fuel faster and speed up its evolution. Now that may sound like a good thing given the age problem I gave you last time, and in fact it is, but it has to be a finely tuned good thing, because the age problem is only a factor of 2 or something, and it's very difficult to tune things that you change the age by only a factor of 2 and not a factor of much more. But in fact, it's even worse than that, because there are some systems whose cooling we know very well. So there are several systems we can use to constrain this, and I'm not going to go through them in detail, but I wanted to just present you with the idea, and then you can go to the literature and look up some of the details, because I think this part is fascinating, actually. The sun is very well known. Its temperature, density, radius, luminosity are well known. And therefore, cooling the sun and changing any of these parameters in disagreement with present observations is a strong constraint. And as I reminded you last time, for better or worse, the present standard solar model, the helioseismology, comparing the predicted vibration modes of the sun and therefore solar sound speed throughout the sun with the observed versus predicted is right now, the agreement is extremely good. It's better than the 1% level. And that has to be taken into account in any picture. Anything that changes that will constrain things. Red giants are not as well known as the sun, but they're a lot hotter, and therefore they're much more sensitive to emission of weakly interacting particles, and therefore you can get, actually, turns out, stronger constraints on red giants than you can from the sun just because they're hotter. But you can use both of these. Finally, white dwarfs, the point there is that you can dramatically alter the cooling time of these objects, and therefore their number density, and to some extent red giants as well. By dramatically altering the time it takes them to cool or burn their fuel, especially if they burn their fuel over a very short time, you can reduce their number density significantly. And if you make the lifetime on a certain branch of the stellar evolution chain go from 1,000,000 years to 10,000 years, you won't see any objects, because at any given time the chance of an object being in that stage is very less small. And I did want to show you this the other day, just to indicate. It's another example of our faith in standard stellar evolution models for certain star systems. This is the number density of stars as you go off the main sequence in a certain chain. This is from a globular cluster again. And the number density, as a function of here, again, a color index, the point is that this number density depends crucially on the lifetime of these stars on different parts of the chain. And what is kind of remarkable to me is that the same stellar evolution models that I showed you before that predict the isochrone so well predict the number density extremely well. And anything you do that cools stars along this region by a greater amount will reduce their number density significantly. And so this is one of the other things that should give you faith in our stellar evolution models. Anyway, let me just give you one example and then we'll move on to another subject. But that's the main thing I wanted to say about this, and let me just give you the example. And the example, of course, is axions, because this idea has been used to constrain axions effectively. What are the kind of existing, given known physics, energy loss mechanisms from stars? Okay? And of course, the one example of a particle that can get out from a star at the speed of light is a neutrino. And so the two standard processes that one has to deal with in terms of cooling stars are the Compton process, where you produce a neutrino-antineutrino pair, and the Bremsstrahlung process, where you produce a neutrino-antineutrino pair. And these processes are relevant for regular stars, and they're used in stellar calculations. Because of the weakness of the process, and also because of the fact that you have a neutrino and antineutrino, neither of them become significant until the star becomes very hot, much hotter than the sun. Okay? But now let's look at the processes that are relevant for axions. And you see, first of all, we have exactly the two same processes. We also have a few other processes because of the axion 2-photon coupling. Now, axions are much more weakly coupled than neutrinos, so why should these processes be relevant compared to these? Well, the fact that they have much weaker coupling says that the process happens more slowly in principle. However, there are two features, and both of them are equally important. The first is that we can emit one axion instead of a neutrino-antineutrino pair, and that's incredibly important, because two-body phase space versus three-body phase space in any interaction like this, the difference of them is significant. And so merely the fact that you have two-body phase space here instead of three-body dramatically increases this interaction rate in principle for the same coupling compared to neutrinos, and therefore for a weaker coupling this process can even dominate compared to that process because of the two-body to three-body phase space. And the other reason that axions can be significant is because of these extra processes. One of the processes that occurs in the sun, by the way, that's very important to think about is the fact that a photon can do something in the sun which it can't do in empty space. It can emit a particle. Okay, it's not allowed to, Lorentz invariance in empty space, but a photon of a given frequency in the sun can have a mass because it's propagating in a plasma. And once a photon can have a mass, it can emit particles. So that plasmon process is very important. So those are just some interesting bits of phenomenology I'll tell you about. And it's for this reason that one can get significant constraints on axions, because of that fact that I told you that producing any energy that can get out at the speed of light is important, and because of the two-body versus three-body phase space factors. So you have extremely long reach, and that's why one can constrain using just normal stars on axion symmetry breaking scale or coupling scale 1 over f of as high as 10 to the 9th GeV, much higher than the weak interaction scale, just because of these facts. Okay, that's everything I wanted to say about constraining weakly interacting particles from stars, but I think it was, as I say, interesting enough, I hope, that it was worth mentioning. Now, let me move on to not neutrino emission to cool stars, but a neutrino emission associated with the processes that powers them. So I'll give you the relevant. I decided I really have to mention solar neutrinos. It would be negligent of me not to mention them. And after all, Douglas Morrison is in the audience. And, the point is that that neutrinos, just as they are for the Big Bang, are an integral part of the energy production process. That one can write the process that powers the sun as 4 protons go to helium, and in the process you emit 2 neutrinos and 25 MeV, which is what powers the sun. And so what we know is that the sun shines. We know the sun is older than 10 million years, and therefore it has nuclear power. And therefore, it emits neutrinos. All of those things are true. Okay, the process is, the thing that determines the solar neutrino problem can just be understood from this. And that is the chain of how you produce helium from 2 protons. Well, the PP reaction produces a neutrino right away, a low energy neutrino. Or you can every now and then, but a much smaller percentage of the time, produce a somewhat high energy neutrino and produce deuterium in the same way. Deuterium interacts with the proton, and this is an integral part of the chain. Every time you're going to get to helium, you've got to go through this part of the chain, which is a rate-determining step in some sense. And it produces helium-3. Then helium-3 can do one of several things. Helium-3 can go directly to an alpha particle, okay? Or every now and then helium-3 and helium-4 can produce a beryllium. Beryllium can then do one of 2 different things. It can capture an electron right away, producing a neutrino of a fixed energy, one of 2 fixed energies, depending upon the energy state it goes into. Okay, but it's a line, as this is. Or it can capture a proton and go to boron, and boron can then decay to an excited state of a different isotope of beryllium plus a neutrino. Very rarely, that's high energy. And then the beryllium will produce an alpha. Or finally, a much smaller percentage of the time, the helium-3 directly can capture a proton and go to helium-4 plus a neutrino, which is very high energy. Okay, so that's the process by which you produce helium and which the sun is powered, and it produces neutrinos. And this is the origin of the solar neutrino problem. This side chain, this process that happens very rarely, but in the process produces among the highest energy neutrinos from the sun. And what was realized, and is truly a remarkable thing, I think, when you think about it, the bravery of Ray Davis, is that you can use the reaction of this neutrino on chlorine to argon, and you can, in principle, in a tank of 100,000 gallons of cleaning fluid underground, you can try and look for an event rate in which 1 argon atom per day is produced in 100,000 gallons of cleaning fluid. Whenever I tell a public audience about that, they titter because it just seems so unreasonable. And it still amazes me that this was ever funded, because it required the techniques of chemistry of one field to look for something extremely exotic in another field. And so it is truly a tribute to that experimentalist that this, whether or not the solar neutrino problem survives. In any case, so having done this is a famous figure and it's of course been, I have the data since then, but it doesn't really matter. This was the data that was taken from the chlorine experiment over many years, 20 years now, 30 years almost. And the numbers were less than the predicted model numbers, which have changed over time, but they've always been bigger than the observations. The other thing that I should point out is that when people look at this, as people who are, we all know that people hallucinate when they are sensorily deprived, and since most particle physicists are sensorily deprived, they tend to look at all data and hallucinate. And if you look at this long enough, you'll look for things like time variation and things. And in fact, you'll see it. And I must say it's rather interesting, because with Michel Spiro and Jim Rich, I once did a project to actually try and prove that there was no time variation in this signal. And we did at one stage, and actually it was published, but actually since then, and we haven't published it, if you actually analyze it any more carefully, you find there is. But anyway, we never bothered to publish that. In any case, what is the implication of that observation and the observations that, I should say what the other observations have been since, because they've added potentially something. And that is, the home state chlorine detector saw much less. The next detector was the Kamiokande detector, which again looked at just the boron neutrinos. Well, actually, the home state detector looks at more than just the boron neutrinos. That's the point. This saw half the standard solar model. This saw a quarter. And this is very intriguing. This already, before the most recent set of experiments, gave you something to think about. Because the the home state detector detects not only the boron neutrinos, but also the beryllium neutrinos. The Kamiokande detector detects just the boron neutrinos, yet the Kamiokande detector gets a higher fraction of the standard solar model than the home state detector does, which is intriguing because the beryllium neutrinos are produced on the way to producing boron. And that is the content of the standard solar neutrino problem right now. How can you get rid of particles, in a sense, which are produced on the way to there? So then the big question was to look at the PP neutrinos. And this is what these experiments did, and they've told us essentially nothing. They haven't illuminated that issue at all, in a sense. I don't want to put them down, but they haven't changed the picture as existed before the experiments were done. So the major implication of right now of the data is that both the beryllium and boron neutrinos are much more suppressed than PP. You see, if those experiments had been done and given a flux which is 0 of PP neutrinos, we'd know there was a problem, because the PP neutrinos are always produced no matter what you do. Unfortunately, what the experiments did was maximally ambiguous. They appeared to show an almost complete PP flux, but a great suppression of these two. But the big thing, and the thing which is the only reason I think most people would argue that there isn't an astrophysical solution of the solar neutrino problem, is that it appears that the beryllium neutrinos are suppressed more than the boron neutrinos, and it's very, very difficult to cook up an astrophysical scenario which does that. Many people, including myself and colleagues, have tried to analyze the data and try and produce things like likelihoods, which is always dangerous. But one of the things one finds if one does this is just, let's just suppress the boron and beryllium neutrinos by a function of temperature. This is from some paper I wrote, but there have been lots of different presentations. Here's plotting the Kamiokande data versus the home state data, which, as I told you, all you need to see the standard neutrino problem, solar neutrino problem. Here's the prediction of the standard solar model with standard solar model uncertainties. Here is just reducing beryllium and boron by the temperature dependence, lowering the core temperature of the sun. Where will it drive you in this curve? The point is it drives you down, but it doesn't drive you anywhere near the data. And this happens to be the prediction of solar neutrino oscillations, and it exactly overlaps the data. Well, when you do that, you can produce numbers. I'm not sure they have any content, but one of the numbers we produced is that the likelihood of this solution versus this solution is down by 10 to the 8th. Anyway, that's the solar neutrino problem. That's all I'm going to say, except to say, how will we know the answer? And of course, there's a time-invariant answer, and so far, and that answer is that the next generation of detectors will let us know. So far, that has been time-invariant. But one hopes that there are two new detectors that really will say something. Super Kamiokande is online and detecting a huge slew of neutrinos per day, 10 or so. If the spectrum of boron neutrinos is observed to be different than you predict, there's nothing in the sun that can produce that. The proof of that is a 1-second thought, or you can read a 50-page paper of John Bacall's recently on that subject. But the content is quite simple. The sun is at a temperature of 1 keV. And there's no way solar processes are going to affect the spectrum of a 15 MeV nuclear reaction at the level when the energetics is 1 keV. End of story. And so if the spectrum differs from what you'd predict, it means there's something different. The other experiment that's online is the Sudbury Neutrino Observatory, which I may talk about in a moment anyway, when I talk about supernova neutrinos. And the point is that detects neutral current interactions of neutrinos. And therefore, it will detect any old neutrino that comes along, in principle, regardless of its type. And if you are getting rid of electron neutrinos and turning them into other kind of neutrinos, this detector will still see it. And therefore, if you see the right number with that detector, but the wrong number with other detectors, you know it's neutrino physics. And I've alluded to the fact that the particle physics solution of this problem is oscillations, so I will just present one graph on that and then move on to another subject. There are two different ways to solve the solar neutrino problem with neutrino oscillations. One is one that has been around for a long time, but Charlene Glashow and I gave a name to, called the just-so oscillations. Namely, if neutrino oscillations, mass oscillations between the different electroweak eigenstates, occur on just the right length scale from the Sun to the Earth, you can end up at the Earth with having far fewer neutrinos of a certain energy, boron or beryllium neutrinos, than you would otherwise. And that looked rather fine-tuned. The other solution, which is really pretty in principle, but in the end turns out to be just as fine-tuned, I'll point out, is the recognition that if you have some mass matrix, neutrino mass matrix with mixings, when neutrinos go through matter, there's an extra term in that mass matrix coming from the forward scattering in matter, the index of refraction. And that extra piece is calculable. Okay? And it's only there because of charge current interactions for electron neutrinos, not muon neutrinos or tau neutrinos. And when you add that extra piece, this will change because it depends on the electron density in the Sun. So you would add an extra piece to the diagonal term there, and you change it, and you find out, of course, that the solution of this for the eigenstates will change depending upon the value of this piece. And in fact, adiabatically, what you can find out is that you can start out, it's a very famous level crossing picture, but I'll show it to you. You can find out that depending upon where you are, if the density is high enough, that extra piece will add a big enough term to the electron neutrino component of the mass that it'll make the electron neutrino more massive than the muon neutrino. But after you're out of the Sun, when the density is down, the muon neutrino will be more massive than the electron neutrino. And as you travel through the Sun, you will go on these trajectories, and of course, when you have a level crossing, you can go from one to the other. And that will produce that will get you from one eigenstate to the other. And it's a beautiful picture. It really is a beautiful picture. The end result is, given all the experiments, that there is some mass range that might solve this, that might be in agreement with all of the experiments. Here is the MSW mass range. The mass squareds are of order 10 to the minus 4 to 10 to the minus 5, large mixing angles, small mixing angles. There are arguments to try and rule these two out. This is favored in a likelihood way, but this is just as, this can solve the problem too. But just to remind you that good old vacuum or just so oscillations involve a mass scale which is much, much smaller, 10 to the minus 10 eV squared. But the allowed range, if you actually look in nowadays, the allowed parameter range of these two solutions in mass and mixing angle is not so different. So if they're both as fine-tuned given the present set of experiments. It's just that the MSW is more generic. But I will also remind you that before MSW in particular, and before this mass range became interesting, because it could solve the problem. This mass range is the kind of thing people talked about. In the old days of GUTS, people talked about, you can do numerology to calculate neutrino masses, which is the only way people can calculate neutrino masses now, since we don't know anything about them. And so you can calculate neutrino masses by calculating them as a ratio of different scales, numerology. And if you put the GUTS scale in calculating neutrino masses, you'll find masses that are this small. Okay? If you look at smaller energy scales, you'll find masses that are larger. And so we don't know the answer. And I personally, since I happen to like just so neutrino oscillations, want to remind you that there's nothing intrinsically bad about having neutrino masses as small. In fact, there may be intrinsically good things about it. Okay, that's it for solar neutrinos. I want to turn to supernovae. And the reason I want to turn to supernovae is just like the case of stellar cooling. There are some truly remarkable things that any physicist should be thrilled to hear about supernovae. So those are the remarkable things I want to talk about, and I don't want to dwell on the fine details. The supernovae are really remarkable objects, and so everyone should know about them. The point is that the light in a supernova, which is what makes everyone so excited originally, is really just a sideshow. A very small percentage of the energy goes into photons for reasons I'll describe in a moment. The dynamics of a supernova, it is an object whose dynamics is completely determined by neutrinos, which itself is a remarkable statement. It's the only such object I know of in the universe. And the energy emitted in neutrinos is closer to 10 to the 53 ergs compared to the light. What I mean by the dynamics, I mean the time scale over which the star collapses and forms a neutron star is completely determined by neutrinos and their cross-sections, as you'll see. And not only is that a remarkable feature, but therefore, because of this, supernovae are I've used the word incredible 3 times because I want to indicate how incredible it really is. They are incredible sources of neutrinos. They are great neutrino accelerators, if you wish, and therefore they're both affected by the properties of neutrinos, because the dynamics is completely determined by neutrinos, and therefore one can use the dynamics of supernova to constrain neutrinos. But they also produce a neutrino beam, which you can then use to test the properties of neutrinos. And let me give you two extreme examples of this, and then just show you why neutrinos affect the dynamical timescale of supernovae. And then I want to give you another object lesson in why to be suspicious of certain things. Okay? The first extreme example was supernova 1987A, which gave us a beam of neutrinos. And one can do the following calculation that asks if it's a calculation that's simple, and therefore millions of people did it and almost an equal number published it. If the neutrinos have a mass, then they're traveling less than the speed of light. And therefore, the time it takes them to get here from a distance of 150,000 light years will depend upon their energy. And therefore, neutrinos of different energy will come at different times. And this is a calculation for the time delay. It's 2 seconds for sort of a 10 MeV neutrino if it has compared to a 0 MeV neutrino. Compare a very high energy neutrino if it has a mass of 10 electron volts, and this is the distance supernova. So this means that from the fact that the supernova signal was a few seconds, you could constrain the neutrino mass. The naive constraint, which was published immediately, was something like 8 electron volts. When you put in the details, and a lot of people worked very hard to put in the details, and over years, and in fact, I must say we wrote a paper 5 years afterwards adding to that discussion, I hope. But, and the bound is now 20 electron volts on the mass of the electron neutrino from this analysis. Okay? It went from 8 up to 25, and I think by doing some refinements from Monte Carlos, we reduced it to 20. This is one thing. But at the other extreme, I want to point out you can do other extremely interesting things. And another interesting bit of whatever is the fact that this is the Lorentz time, the special relativistic time delay, if you want to call it that. What is truly remarkable about the supernova is that the gravitational time delay exceeds the special relativity time delay by a huge factor. The gravitational time delay is the Shapiro time. Things take longer to travel in a gravitational field than they would otherwise. And if you calculate that, just given the known potential of the galaxy, you find out that the gravitational time delay, the fact that general relativity exists, the extra time it takes neutrinos to get from the supernova to here is 6 months. Much bigger than this measly thing that comes from the neutrino mass. So, one of the interesting things I like to say is if it weren't for gravity, supernova 1987A would have been supernova 1986C or something. But as a result of this fact, you can actually put very strong constraints on the weak equivalence principle. It's something we realized a while ago. Because, of course, the neutrinos are seen within several hours of the photon. And therefore, one can use the fact that they therefore are both changed by roughly the same amount in a gravitational field, a few hours over 6 months. And that gives the strongest constraint I know of on the weak equivalence principle for relativistic elementary particles. So it's kind of interesting, the kind of things you can do. But let me just spend a minute showing you why neutrinos affect the dynamics of supernova so much. And it's, again, if you haven't heard this, and people who are younger than a certain amount who didn't hear the thousands of talks after 1987A might not know this fact. When a star collapses, I remind you, the only way it can collapse is by cooling. Okay? And so what originally happens is that a star gets ready to collapse if it's big enough when it burns out its nuclear fuel. Okay, and when it's burned out its nuclear fuel, it does this over a course of 10 to the 7th years for the final stages of its collapse. It is ready then to just go boom, and at a certain point, even the electron degeneracy pressure is not big enough. When those electrons become relativistic, you can show even the quantum mechanical degeneracy pressure is not enough to hold the system up, and it collapses. In the final stages, when it goes from a size of 10 to the 7th centimeters down to 10 to the 6th centimeters, the dynamical time scale is a millisecond. And that process should happen, therefore, in a millisecond. It doesn't. And it doesn't completely because of neutrinos, which is, for anyone who's ever thought about neutrinos as a particle physicist, it's an amazing fact that the density of this system is high enough to trap neutrinos. Okay, the mean free path of neutrinos in this object is smaller than the size of the object. And therefore, the only way, I remind you, this system can collapse is release its gravitational energy. The only way it can release its gravitational energy in a short time is by emitting neutrinos. And if the neutrinos weren't trapped, this would happen in a millisecond. But it happens in order of seconds. Okay? Precisely because of neutrinos. And that's why the neutrinos affect the dynamics. That's one of the reasons. That's the important dynamics. They may also affect the visual dynamics. It's been very difficult to make the irrelevant part of a supernova, the outer core part of it, actually blow off. And it may be that neutrinos coming out of here actually deposit enough energy in the outer core that's blowing off to allow it to continue to blow off, which is another important thing, but that's of main interest to supernova people and not to particle physicists. But it's this fact that tells you the dynamics is affected by neutrinos. If you change the properties of neutrinos, you'll change that dynamics, and that's where people get constraints on neutrino physics from the shape of the supernova signal. Okay? I just now want to close my discussion of supernova neutrinos, because I said the things I think that are mostly interesting, with one last thing, which is the next supernova. People got so excited from 18 events. They said, what about the next supernova in our galaxy? Okay, or actually, this one wasn't in our galaxy, but the next one in our galaxy would, at a distance of 10 kiloparsecs, produce 1,000 events in Kamiokande or 10,000 events in super Kamiokande. You can imagine the number of papers that could be written and the number of particle physicists that could be employed. And so it was very exciting. And I just want to point out two things. One which is self-serving and the other which is, I think, of more general interest. That is that if you're careful, one can do very interesting things with the next supernova and do things that you think naively could not happen. And I just want to give you a brief, well, maybe I'll give you the story in words and just present one transparency. Super Kamiokande will have 10,000 events. Okay? Now, you can do an analysis and say, well, just again, a kind of dimensional analysis idea. How much of a time delay will be introduced by neutrino mass from a neutrino coming from 10 kiloparsecs away, and as a function of energy, here's the time delay. And you see if the average energy is greater than, something like 15 to 20 MeV, then time delays greater than the second will only be introduced by, masses bigger than about 30 electron volts. Now, we know that the electron neutrino hasn't got such a mass, so we're talking about mu1 and tau neutrinos. Well, you can show that of the 10,000 events or something that super Kamiokande will see, all but about 300 or so will be due to electron neutrinos, or electron antineutrinos. And therefore, you might say that it's therefore going to be impossible from the signal to actually see any evidence of the mu1 tau neutrino mass if there is one. And that's a naive idea. And the point is, it is naive. It's kind of interesting that you can do better. And I just wanted to indicate that one should carefully think about these things in advance of doing experiments, because you could do better. And the idea is just simply the following, and we spent a year or so doing a Monte Carlo to prove this fact, is that there are different scatterings that happen in a water detector. The predominant one is antineutrinos off protons. That's the biggest cross-section. That's the reason that almost all of the events in super Kamiokande are antineutrino events. Well, when an antineutrino of a mere 10 or 20 MeV hits a 1 GeV particle, the stuff that comes out that you see, in particular an electron or a positron, can go in any old direction because it's hit this house. Okay? However, if a 10 or 20 MeV neutrino scatters off an electron, which is a mere half an MeV, the product will go forward. Now, the only reactions that mu and tau neutrinos have in a water detector is the neutral current scattering off electrons. Okay? And therefore, all of the neutrino and mu1 neutrino and tau neutrino events will be forward in some sense, whereas the antineutrino events will be all around. Okay? Now, you might say, okay, well, let's just look at the forward signal. But the problem is, and look at the nature of the forward signal, and therefore look for a mass. But the problem is, you don't know what the supernova neutrino signal was like until you measure it. But the great thing about a water detector is you have the other signal. and you have the 10,000 events in the other directions that tell you what the supernova neutrino signal is like for a massless particle at this level. An electron neutrino being less than 30 electron volts will tell you what the signal looks like without any time delays. So you can use that to normalize the signal and then look in the forward direction, and it's truly remarkable to me, and we've shown it to be true, Monte Carlo, that you can distinguish the effect of 50-odd events out of 10,000 by using that kind of analysis, which is interesting. So just to give you hope that you might be able to look for interesting tau and mu neutrino masses. But the other thing I want to point out to you is to always be wary, and this will come back to us in the last one or two transparencies of this lecture, I think, of theorist predictions, of experimental observations. Okay? I'm going to protect the authors of these papers by not telling you who they are, but here are some very careful calculations of what the neutrino signal should look like for a galactic supernova, based on real stellar collapse calculations. And this is what was predicted as the event rate in Kamiokande and SNO, and I have several of them, but they all look the same. And what was pointed out was the remarkable thing was you might even be able to find a mass for the electron neutrino, or because you could look at, there are all these little wiggles, and if you have 20 electron volts, they're going to smear out these wiggles. Okay, and this is the kind of thing one often sees in advance. Okay, this is a theorist's picture of what the event looked like in a detector. But of course, in a real detector, you have a lot of things like the fact that you don't detect the energy. The output detected energy is not the same as the input detected energy. There are backgrounds. There's a huge number of things. When you actually put it in, this is, I remind you, over about 0.4 seconds. Okay, or a range, an interval of about 0.2 seconds. Okay, here's what the actual signal in Super Kamiokande would look like based on our Monte Carlo for a completely smooth signal over 0.2 seconds. And you see the point is that you cannot in any way, this is with a 20 electron or 50 electron neutrino mass, electron volt neutrino mass, and this is nothing. There's no, in the actual experiment, this kind of fine resolution is a theorist's dream, but the actual experiments cannot detect this. And so you have to, if you're going to do anything realistic, when you want to constrain future experiments, you have to think about what the actual future experiments are really going to see. And this is important because we will often hear very optimistic views of what can be done in the next generation of experiments. And it's great because it motivates doing them, I suppose. But one should always be prepared for not being able to see that stuff. Okay. Now I want to move on. Okay, that's everything. That ends the subject of stellar evolution. And the topics I wanted to talk about, constraining elementary particles and the kind of neutrino physics you can do. And now I want to move back in the last part of this talk, in the last half hour or so, to two topics. One, what I promised you, the discussion of the baryon, of Big Bang nucleosynthesis and the baryon crisis. And then I will have some discussion of large-scale structure in COBE, because I think you can't have such a lecture without mentioning it. So let me give you a 5 or 10 minute review of the physics of Big Bang nucleosynthesis. The reason is that this is really the progenitor of all modern particle astrophysics. This was the first example of using microphysics and combining it with astrophysics in cosmology in a real sense. And it's not too surprising, therefore, that it comes down to the same thing I told you about earlier. The most important equation in cosmology and astrophysics is the Boltzmann equation. All of the light element abundances can be understood in some sense in terms of the Boltzmann equation, which I gave you before in the first lecture. And I told you that when the interaction rates are less than the expansion rate, you get decoupling. And that means that the distribution functions will no longer follow the thermal equilibrium values. And what are the thermal equilibrium distribution functions? Okay? Well, for a massless particle, it tells you that the number density goes like T cubed. And for a massive particle, it tells you the number density goes like T cubed times some Boltzmann suppression factor. Now, so after decoupling, the distribution functions no longer follow these things in principle. What do they actually look like? Well, there's two things that are kind of interesting to note. One is, well, here's what the distribution function looks like for a massless particle when it's in thermal equilibrium in an expanding universe. Here's what it looks like afterwards, exactly the same. A massless particle will have the same thermal the same distribution function after it goes out of thermal equilibrium as before, just simply because momentum, it's massless, and its momentum redshifts like temperature, like the expansion rate. And therefore, a massless particle distribution will look exactly the same as it did before. Its temperature will, however, fall as 1 over r. And therefore, if there's any entropy generated later on, its temperature will be different than the other stuff, whose temperature will not go as 1 over r, because the entropy will feed into it, which is the origin of the fact that I told you neutrinos have a different temperature than photons. For a massive particle, when it's in thermal equilibrium, its number density over the number density of photons goes like e to the minus m over t. But after it decouples, this is a dramatic difference, it no longer falls that way. It stays at e to the minus m over t decoupling. That was important for determining the relic abundance of WIMPs, you'll remember. But that was by far not the first time this was applied in physics. In fact, the most important, far more important than the abundance of WIMPs, is this calculation, because this is responsible for our existence. Okay? If it weren't for this fact, we wouldn't be around, because nothing other than protons would be around. Okay? Because of the fact that neutrons and protons are in thermal equilibrium at high temperature, and neutrons weigh more than protons. And therefore, as the universe cools, the neutron to proton ratio will fall as e to the minus m over delta m over t. And delta m is an MeV or so. And when the temperature is our temperature, there should be no neutrons left in the universe. And certainly when the temperature is even a tenth of an MeV, there should be no neutrons left. And nothing to form heavy elements. So our existence depends upon the fact that that interaction, which is a weak interaction, decouples. Okay? At a temperature of around an MeV. And so, in fact, this is, for the most part, the entire content of primordial nucleosynthesis. As you follow temperature, this is what the neutron to proton ratio should look like. But because of the fact that the weak interactions decouple at around 2 MeV, the neutron to proton ratio smooths out. And then, of course, neutrons will decay. And that means there's some neutrons left. And every one of those neutrons that's left will combine with a proton to form helium, to first approximation. And that's the entire physics behind this, essentially. And from that we can understand the entire phenomenology of BBN. So here's the time picture of what happens in Big Bang nucleosynthesis. Initially, you start out with protons and neutrons as your building blocks. Okay? Now, and because of the fact that the neutrons have frozen out, they're not falling with an exponential, thankfully. Okay? They're decaying with some decay time as the temperature falls, but that's relatively slow. Now, as I showed you from the sun, however, before protons and neutrons can build up to helium, they have to produce deuterium. So if the protons and neutrons could just directly go to helium, then the helium abundance, as the universe cooled, would increase dramatically. This is what it would be if it followed its thermal equilibrium value. But of course, you can't produce helium until you first produce deuterium. And therefore, until you've produced enough deuterium, the helium is held back. And then once you've produced enough, the helium can go up, as high, it can go up to the value which essentially all protons and neutrons are wrapped up in helium. And that's the reason why one can constrain parameters such as omega baryon because of this. Because of this rate determining step. Because if you start out with more protons and neutrons, then you will push the time at which deuterium, if you start out with more of these, you'll make more deuterium. And you'll push the time at which there's enough deuterium to make all the helium you want to earlier times. And if you do that at earlier times, fewer neutrons will have decayed, and you'll end up with more helium. Therefore, as you push omega baryon up, you will end up with more helium. That's the physics. Also, since deuterium is an intermediary in that process, if you more effectively burn deuterium to produce helium by pushing omega baryon up, you'll end up with less deuterium left over. So deuterium will fall monotonically as you increase omega baryon, and helium will increase monotonically. Okay, that is the content when you actually solve things, and this is an old picture. You get one of these famous curves. And this is the abundance of helium as a function of omega baryon, presented in a weird way. It's related to the number of baryons or the number of photons in the universe. And you see that as you produce more helium, as you have a bigger baryon abundance, you will monotonically produce more helium. And the reason is just what I showed you. On the same token, you'll produce less deuterium and also helium-3, because both of those are intermediaries on the way to producing helium. So as you more effectively produce helium, you produce less of these guys. Lithium is more complicated, and one can describe that equally well, but I don't think I will for lack of time. By the way, you can also understand the famous fact that you can understand why, as you increase the number of neutrinos, you produce more helium. As you increase the number of neutrinos, you increase the number of particles in the radiation gas at earlier times, and therefore you increase the expansion rate of the universe. As you increase the expansion rate of the universe, you make the time at which the weak interactions decouple, or the temperature, higher, because the expansion rate is faster. Therefore, the weak interactions decouple earlier. And therefore, the neutron abundance is bigger, because it's e to the minus m over 2t decoupling. And since you have more neutrons, you end up with more helium. That's simple. It's true for that's why this doesn't mean neutrinos. It means any relativistic particle in the radiation gas. Any particle you want, neutrinos, new scalar particles, anything will be constrained by this. And that's one of the reasons why you can use this to constrain particle physics up to the gut scale in some sense, to the extent that it produces relativistic particles. Okay, well, that basically brings you up to about 5 years ago. Or 10 years ago. What's the difference? What's been new in the field since then? Well, the one thing that happened between here and, say, 1987 or so, and this is actually 1994, is that these theoretical predictions turned into ranges. Okay? And we spend a lot of time to that for the same reason as we looked at the age of globular clusters. And the point is that the predictions in here involve nuclear reaction rates, which are measured in the laboratory and therefore have uncertainties. And so the predictions are not lines, they're bands. But what do you do with this? Well, what you do is the following. This is my summary. BBN, or crisis, what crisis? BBN provides an upper limit on omega baryon. The upper limit, which is the strongest upper limit on omega baryon we have, and one of the main reasons why we still believe that there is non-baryonic dark matter in the universe. And it comes from the following. The helium abundance increases as you increase the baryon density. Therefore, if you can put an upper limit on helium, you can put an upper limit on omega baryon. You can also put a lower limit on omega baryon, okay, which is interesting. I mean, we know the lower limit's coming from observation. I already gave you that number by looking at how many baryons there are in the universe that you can see. But the key question is how many baryons exist that you can't see. And for that you want a lower limit. And you do that from the fact that deuterium and helium-3 go down as omega baryon goes up. And therefore, if you can put an upper limit on these guys, then you can put a lower bound on omega baryon. This was what was done for 20 years or so in the Big Bang trade. And it is wonderful as long as x is bigger than y. If x is bigger than y, then you have a range, and you call it great success. However, if the lower limit is bigger than the upper limit, as, for example, was the case with the age problem I talked about, then people get worried. So the change that's happened in the sociology has been that a success has turned into a worry. Okay? Here's the context of this in modern. Let me see if I got this right. Yeah, probably. Okay, here are what some people would have argued were the allowed ranges of these primordial elements: helium, deuterium plus helium-3, and lithium. And the important thing is, if you look at this allowed range tells you that you get an upper bound on omega baryon of some number. That omega baryon has to be less than this, because you see, if it was bigger than this, you'd predict a bigger helium abundance than you can account for. So that gives you an upper bound on omega baryon. The lower bound on omega baryon comes from the fact that you believe that deuterium plus helium-3 is less than this number, and therefore any smaller value than this for omega baryon would be in disagreement with the observations. And actually, when we redid this in 1995 or so, with new neutron lifetime estimates and some new nuclear reaction rates, and pointed out at the time that the success was already becoming embarrassingly good. Namely, you could make this range extremely small. Of course, that naturally then led people to suggest that the range would evaporate completely. Because what if, instead of this being the upper bound on helium, what if this is? And what if instead of this being the upper bound of deuterium plus helium-3, actually I should put it down about there, this is, then you get the fact that the lower bound on omega baryon is here, and the upper bound is here. And that's the crisis that was alluded to in 1995 and 6 in a lot of papers. Of course, there is no such crisis. The reason being that even these estimates are based on observations, not experiments. And therefore, the dominant uncertainty is systematic. Moreover, in fact, they're not even based on observations. Just to remind you, the helium abundance comes from the following. The abundance of primordial helium that's actually inferred in the universe comes from doing something like this. And I have a bunch of different graphs, but one we'll do. One looks at systems whose heavy metal abundance, oxygen, nitrogen, heavy metal in stars means anything heavier than hydrogen. Okay? And one looks at systems that have a smaller and smaller abundance of those materials. Well, those systems should be older because these oxygen and nitrogen and everything else are produced not in the Big Bang but in stars. So in order to have a certain abundance of this, the gas will have had to have gone to a star first before it comes into this star. So if you look for systems that have lower and lower abundance of these things, you're looking at objects which formed out of a primordial gas, or as primordial as you can get. And then you measure the helium abundance of those. And then you do an extrapolation. I come back to my Vellelin's law that I said at the very first lecture of experimentation, where if you want to draw a straight line, make sure you only take 2 data points. Well, you see here that things are much more sophisticated. This is not a straight line. It's a quadratic. It's a quadratic because it fits better than a straight line. It's not a cubic because a cubic doesn't fit any better. Okay, that's the theoretical input. Okay, when you do that, you derive a number which is extremely precise. You just extrapolate to 0 and you derive a primordial value. Okay? That's the way this is done. And that's how you end up with precise numbers on the helium abundance. Well, you might worry about this process, especially since one has no fully theoretical reason why this should depend quadratically on this. First. Secondly, you look at this and you see they're scattered. You might wonder whether a realistic value for the light element of the abundance of helium might not be this 0.226 from this case, plus or minus 0.006, but might in fact be the scatter on the lowest point, which is already much bigger. But that would be worrisome, but it's even more worrisome because in fact the helium abundance that you get from here doesn't come from observation. No one observes the helium abundance in these systems. This is inferred. You never observe the abundance of neutral helium, which is most of the helium. You only observe the abundance of ionized helium. And from that, you take an atmosphere model and say, for a given amount of ionized helium, how much neutral helium is there? So this never comes from an observation, but an inference. And that, of course, is certainly subject to dramatic systematic uncertainties. Well, if I haven't convinced you, then that arguing that the bound on primordial helium is 0.232, which is what some people would claim nowadays, or 0.234 rather than 0.24, may be overstating the case. Let's see. This. Yeah, you're right. In fact, in this picture, I should show you a real quadratic in a logarithmic scale. This has to be refined to this, and then it's a quadratic fit. Okay, but you're right. You caught me. Okay. The key point is that there is no, I repeat, no real theoretical understanding of the relationship between the abundance of helium and the abundance of oxygen and nitrogen. It's a phenomenological fit. Okay. So you might say, well, okay, therefore it's clear that, this bound on helium, the helium, and people have now realized and argued, as some people would have argued before, that even 24% is probably not conservative enough. Some people have said 25%, 26%. And then there's not going to be any crisis, no matter how low the deuterium abundance is. And you might, given that, argue that there's no bound on omega baryon from Big Bang nucleosynthesis. And I do want to disabuse you of that notion. Because I do believe that the upper bound on omega baryon from Big Bang nucleosynthesis is still robust in spite of the systematic uncertainties I've talked about. And the answer really still is that deuterium gives an upper bound on omega baryon because deuterium is fragile and it is destroyed in stars. It can never be produced in stars. It's always burned because of its weak binding energy. And therefore, if you look at the deuterium, if you can measure the primordial deuterium abundance, you always have an upper limit. Okay? And a lower limit. And it's, let's see. You have an upper bound on omega baryon just by knowing the deuterium value. Okay? And knowing the deuterium value can't be less than or greater than some number. And that was true 20 years ago, and it's still true today. And in fact, I was going to present to you in a somewhat detailed analysis to show you, when you consider the uncertainties in all of the light elements, helium, lithium, and deuterium, which we've done, that you get a bound. But the bound is essentially the same one you get for deuterium, more or less. But when we've analyzed it, this is the number that we've come up with, and that we came up with that 4 years ago. And it thankfully is the only upper limit on omega baryon which has now not been violated by the data, by the Big Bang nucleosynthesis data. Namely, even the new numbers on deuterium, I'll show you in a moment, don't violate this upper bound. Because I believe it. In order to violate this upper bound on omega baryon, not only would helium have to be subject to huge systematic uncertainties, but deuterium would be, and lithium. All of the elements come together at this value. So this could be wrong, but only if every single thing is wrong, which is possible, but not likely. Okay? Now, what is the new experimental content? The new stuff, which has caused a lot of interest in the last year, is that people have actually measured, or claimed to measure, the primordial deuterium abundance. You do that not by looking at systems that are close by, but if you look at a quasar, which is very far away, and it passes through hydrogen on the way to us, and that light gets absorbed, and you see a huge trough due to hydrogen. Well, if the trough is big enough, deuterium will produce a trough, and if deuterium is down by 10 to the minus 5 compared to hydrogen, it'll produce a little trough, unless you have a lot of hydrogen. But if you have enough hydrogen to absorb the light, you will be able to see the deuterium absorption line. It happens to be in Doppler space, 82 kilometers per second shifted away from the hydrogen line. And this was measured first by a group and they came up with a remarkable number. The number was 19 times 10 to the minus 5. Now that's interesting because if you remember from my last curve, the upper bound on deuterium plus helium-3 abundance was said to be 10 to the minus 5. And they found a primordial abundance which is twice as big as the upper bound. Very exciting. Well, of course, this was from one system. Now the question, of course, is, hydrogen clouds are not these nice objects that just sit there. They're lots of little lumps. What if you happen to have a lump in a complicated hydrogen cloud which is moving at about 80 kilometers per second relative to the hydrogen cloud? It will mimic this. With one system, you can never know the answer. So immediately people said we should look at many systems, which is the right answer. You should look at many systems. And what's been interesting is there have been many systems looked at. And another group looked at a bunch of signal systems and found a value which is incredibly small compared to the primordial upper limit of 10 to the minus 5. I didn't put the exponent here. It's 2.4 times 10 to the minus 5, not 19 times 10 to the minus 5. And so it's an order of magnitude smaller than this, and it's also a factor of 5 smaller than the upper bound that I gave you earlier. And if you actually look at the graph I gave you for Big Bang nucleosynthesis, a value of 2 times 10 to the minus 5 is out here, meaning a very high omega baryon density. Okay? Now, what's been interesting in the last year, first of all, these are the two numbers that are quoted because they're the loudest. But one should note that there are probably 11 different measurements I know of, and they happen to fall in between this range. Okay? So what I'm about to say is should not give you the idea that something definitive has yet resulted. But in Christmas time, these people retracted their number, okay? Which is interesting. Because now that means that there's stronger evidence that the deuterium number is small and omega baryon is big. But I want to point out to you, it's still from a few systems. And no sensible person should accept this as the real number until probably 50 or 100 systems are measured. But when they are, we will unambiguously know the primordial deuterium abundance, which is a very important thing. Because once you know that, forget the whole curve, you have a point. Once you know the primordial point, you know omega baryon, and then you can use that to test everything else. But the other thing I want to point out to you is that in spite of what some people might claim, this number is not in violation with the upper bound that sensible people should have given on omega baryon before, namely us. This value would correspond to something near the upper bound, but 0.024, h to the minus 1. What's disturbing about this, or interesting, is that if h is 50, which some people still like to believe in spite of the fact that there's no observational evidence of that fact anymore, or very little, but it's hard to give up pretty notions. If you put h as 50, then in fact, sorry, this is h to the minus 2, which should make things a little better. If h is 50, then the abundance of baryons gives an omega of 0.1, which is frustrating because that's comparable to the omega in galaxies and their halos. You see, if Big Bang nucleosynthesis could argue this was a factor of 4 smaller, then we could definitively say that halo dark matter is not baryonic. And that would be remarkable and wonderful. But what the number, as always seems to happen, comes in the frustrating region where you can't yet, therefore, say that baryonic halos are non-baryonic. In fact, it argues that most of the baryons in the universe must be dark, because the visible component is an order of magnitude smaller than this. And therefore, we would expect to see lots of dark matter in the halo, if not the whole thing. And we should see some machos, therefore. So it's interesting. The other thing that's come up that's been interesting in the last year, although I expect it's probably wrong, is some people have reanalyzed the data and now argue that the helium abundance is bigger than they thought before, which of course is what I told you would have to happen anyway. But that's interesting. So that's the content of this. But that's not the baryon crisis. There's no crisis there. It's interesting, but no crisis. The crisis comes from the same thing I talked to you about earlier, X-ray clusters. I remind you that if you can look at a cluster of galaxies, which is the biggest mass distribution we know of, most of the mass in that system comes from hot gas. This is like in a cosmology meeting. Now, if you can measure that hot gas, then you can tell a lot about the system. In particular, if you assume this wonderful thing called hydrostatic equilibrium, which is that pressure balances gravity, then if you measure the temperature and luminosity of the hot gas, you can invert that and get the gravitational potential well in which that hot gas sits. That gives you two numbers. It gives you the gravitational potential well, which of course is proportional to the total mass of the system. Okay? It also, however, since you measure the temperature and luminosity of the gas, gives you the mass of the gas. Therefore, it not only gives you the total mass, which is evidence for dark matter, but it can tell you the ratio of the gas to the total. And since almost all the baryons are in the gas, it tells you the ratio of baryons to total mass. Okay? Now, if clusters of the largest objects we know of in the universe, and they come from gravitational collapse of the dominant matter, and the dominant matter is dark matter, then they should sample all of the matter in the universe. And therefore, this ratio should be omega baryon if the universe is flat. If the universe is flat, then M total is a critical density. And therefore, this ratio should be M baryon if the universe is flat. If the universe isn't flat, it still gives you the fraction of baryons, the primordial fraction of baryons compared to the total matter in the universe. Now, what was pointed out a few years ago is that this number is embarrassingly large. Looking at the Coma cluster, which is one of the rich clusters, for h of a half, it was discovered that this ratio is 25%. A whole slew of other people analyzed things in more detail, and I was going to show you that data. Well, I just, well, here's one subsample of that data. This is for a whole bunch of clusters measured out to a certain density contrast in the cluster. You can measure the gas mass to total mass fraction, and you find out, that the numbers are 15 to 20%. Now, unfortunately, or fortunately, this has an h dependence, because you're asking how much mass is in a given scale size, and the given scale size depends on the actual physical size of this cluster, and the physical size of the cluster depends upon how far away it is, and how far away it is depends on the Hubble constant. So the actual dependence is h to the minus 3/2. About 2 years ago, when Mike Turner and I looked at this, we came up with this bound based on this. More recently, Gus Everard, who's one of the authors of these papers analyzing how to analyze the gas fraction in a cluster, has looked at this and argued from the current data, the number is actually 0.06 plus or minus 0.003. Much smaller range much more stringent range than we said. But I don't care. Let's take this, even this large range gives you a crisis, because this is, I remind you, for a flat universe. The bound from Big Bang nucleosynthesis, which I said was absolutely correct and inviolable, was 0.26 h to the minus 2. That's the upper bound. The lower bound from clusters is 0.05 to 0.08 h to the minus 3. And again, the lower bound is bigger than the upper bound, which is always an embarrassment. Except, you can calculate for h of 20, the two will be consistent. So, perhaps the Hubble constant is 20. Well, it's possible. It would solve a lot of problems. No observational evidence for it, but that doesn't, as has been pointed out, I think someone was telling me the other day that Vera Rubin looked at the data, at all the observational data for the Hubble constant in the year 1970 or something, and there wasn't a single measurement less than 100 at that time. Anyway, but it's a problem. How do you get out of the problem? It would have been nice if I put that. I thought I did in one of these transparencies. Maybe I didn't, but it's simple to say, is, well, if the universe isn't flat, then this isn't omega baryon, but it's just a baryonic fraction. And if omega is much less than 1, omega total, then the baryonic fraction times omega total is omega baryonic. And therefore, if let's say omega total is a half, then you can make this range agree with that range. If it's a quarter, it's easy to make it agree. So perhaps the universe is open. Okay? But it's a problem if you want to have a flat universe. That's the crisis. It's really a flatness crisis, if you wish. Okay? And it comes from comparing BBN to X-ray clusters. There are some issues I want to leave you with. Yeah, I'm almost going to end on time today, which is good. First of all, clusters don't all have the same value. Some have a value which is much, much smaller of baryon to total fraction than the richest clusters. And that implies that there's something non-gravitational at work here. And if there's something non-gravitational at work here, maybe there's something non-gravitational at work in making clusters, in which case the argument that clusters are fair samples of the mass density universe may be wrong. So that's a worry you might have. The other worries are, well, if you assume any lumpiness in the cluster, it will tend to decrease the calculation of the gas fraction. So lumpiness will screw things up. The other is the worry I told you about earlier, that gravitational lensing measurements of those same systems tend to give a higher total mass than the X-ray cluster analysis. Well, a higher total mass and the same number of baryons means a smaller baryon fraction. So there's a worry there. But at the same time as I give you those worries, the data is very robust. And what surprises me is I thought as there was more data and more analysis, this problem would go away. Instead, it's gone the other direction. As there's been more data and more analyses, the problem appears to be getting more robust. It seems to be firmer and firmer and firmer as people try and squeak out of it with these issues. People have done very detailed numerical codes and numerical analyses of cluster collapse, and they all seem to give this a complete agreement with what's observed, and it's getting more robust. The other thing you might say is, well, there's another way to solve this without having, there are two other ways to solve this without omega being less than 1. One is, of course, my favorite solution, as always, which is to add a cosmological constant. Because the cosmological constant is a smooth distribution of energy, and it's not measured at all in clusters. So clusters could correspond to the total matter in the universe, which could be a small fraction of the total density of the universe. The other way you might imagine is to have neutrinos, some component of dark matter being neutrinos, because neutrinos are light, and maybe they don't get captured in clusters. Well, the answer is that's wrong. People have done detailed analyses, and even light neutrinos, 1 eV neutrinos, get captured enough in clusters to not affect this argument at all. I mean, I can present to you a graph, which I have here. This is the density in the cluster scale as a function of neutrino mass. And you see that at a level of 1 megaparsec or 1 to 2 where these things are measured, even a 1 EV neutrino is going to change things by a very small fraction, 5 to 10%. Not enough to affect this. It's going to change the density of clusters by a small fraction. Okay, that's everything I wanted to say about Big Bang nucleosynthesis. In the last 5 to 10 minutes, I want to just give you a quick overview of what the issues are for large-scale structure so that I can conclude with some statements about the future. The omega, let's see. Large-scale structure gives you another omega problem. And large-scale structure also suggests that perhaps omega in clustered matter is much, much less than 1. And I want to just quickly show you that. Even though I've left it to the end, because I didn't want this lecture series to be totally a lecture series on cosmology, it is the central question in cosmology, okay, is this. This is what the universe looked like at t approximately equal to 0, based on all measurements we can make. It's Kobe. This is the structures that existed in the universe. Here's the universe in 1996 when I drew this picture. Okay? There's structure. There are baryons. The central problem is to understand how you get from the first picture to the second picture. Okay? And the way one understands this, and I can do this in one transparency. I really am almost done, so don't worry. Is by recognizing that we believe that structure forms by gravity. Now, this is a very complicated subject in general, but there are a few things that aren't so complicated. And there are two that I want to talk about. One that relates to this, and then one that relates to Kobe and Kobe's successors. The first is that if gravity governs the formation of structure, then to understand the structures we see today, those structures had to come from primordial density fluctuations. And the first question you then ask is, what are the primordial density fluctuations? And you do one of two things. You either guess or you have a theory. It turns out that both give the same answer, as you might expect. The guess was, although it's rather interesting that I just saw a paper recently that contradicted this. The guess was that when God created fluctuations, he didn't have any scale size in particular, or she didn't have any scale size in particular that she should create them at. And therefore, there should be a scale-free spectrum. Delta rho over rho in Fourier space should have no preferred scale. It should be a power law. Now, the second thing comes from observation. If there is a power law, it must be near 1. Why? Because if n is big, then this blows up for large k, small wavelength. That means you start out with a universe full of primordial black holes. Such a universe isn't allowed. If n is very small, then this blows up for small k. That means you end up with a universe with inhomogeneities that are huge on large scales. We know that's not the case. I showed you that in the first lecture. Therefore, n can't be very different than 1. That's the argument. Now, that's the primordial spectrum. That's not the spectrum we see. This is the primordial spectrum. It looks like this. This is the spectrum we see. Why is it? This turns into this just because of causality, essentially. That's why I wanted to do it here. There's nothing, no fanciness. There's some model dependence, but not much. Large k, up here, means small wavelengths. Small wavelength fluctuations know their fluctuations before large wavelength fluctuations. Why? Because of the speed of light. If the universe existed for a short time too short for light to travel across a fluctuation, then there's no way a fluctuation can know it's a fluctuation. But small wavelength fluctuations know their fluctuations and can respond with microphysics. Small wavelength fluctuations, therefore, would come in the horizon at early time and can respond. Now, I told you in the very first lecture that if there's one photon in the universe today, it will at some early time, it will dominate the energy density of the universe. And that's true with the number of photons we have today, because the photon energy redshifts like r to the minus 4, and the matter energy redshifts is r to the minus 3. Therefore, there had to have been a time if matter dominates today, no matter what its ratio with photons, there had to have been a time when the universe became radiation dominated as you go back in time. That's a very important time, because small fluctuations that are in the horizon in a gas that's dominated by photons, which has a high pressure, will oscillate. Moreover, if they're coupled to the photons, those photons will dissipate and those fluctuations will die away. So any fluctuation which came in the horizon early will die away. That means large-scale fluctuations will die away, and you'll turn this thing into this thing. The key point is, when does it cross over? It crosses over for the wavelength that comes in the horizon at the time the universe becomes matter-dominated. Okay? And what scale is that? In physical scale size? Well, it depends clearly on the matter density of the universe today. More matter, an earlier time when the universe becomes matter-dominated. So it comes as omega matter h squared. But then to connect wave number with physical size, you always have to use the 1 over the Hubble constant, because it determines the scale size. So you multiply these two things, and you find that the wavelength where things should turn around is proportional to omega h. So you actually measure the spectrum of fluctuations in galaxies by one of many different ways, by 2-point correlation functions, by angular correlation functions, whatever, and you ask when it turns over. And all of those measurements say the same thing, that the combination of omega h is 0.2 to 0.3. This is an interesting problem. Okay? It's a very interesting problem, because it means if h is 0.6, then it's very hard to have omega equal 1. Another bit of evidence that that either the universe is open, or I remind you that you could solve this with a cosmological constant, because a cosmological constant wouldn't contribute to any of this. Okay, so the last 2 minutes I want to show you pictures of the other bit of large-scale structure coming from COBE. COBE was the biggest revolution in modern cosmology for 3 reasons that I know of. First of all, until COBE, one wanted to know what the primordial spectrum of fluctuations was, but one didn't have one never saw primordial density fluctuations. You saw galaxies. Galaxies aren't primordial because causal physics has formed them. So they're a very indirect probe of the primordial spectrum of fluctuations. For reasons I'll show you in a second when I show you the picture, COBE gives you a normalization of primordial density fluctuations, which are unaffected by mere physics since the Big Bang. Okay? And not only are they primordial, but it gives you the overall normalization. That's the other thing. When you see galaxies, you only see matter, visible matter. But there's always this uncertainty of how it relates to all of the matter in the universe. Is the total amount of matter clustered the same way galaxies are clustered? Don't know. But when we see COBE, we're seeing all the matter. And therefore, it gives us something to normalize to, which we then can connect observations to. Until that point, we connected observations at some scale, 8 inverse megaparsecs, for some historical reason where galaxy clustering started to happen. But one never knew whether that was whether that normalization was correct or whether it should be pushed up or down. With COBE, one can normalize it. Finally, one has a new test of quantum mechanics also, which is interesting. Okay? Because after all, the COBE measurement of the spectrum, of the primordial spectrum of microwave background spectrum, is a black body spectrum. And it is the best measured black body in nature. Okay? It's better than any black body that's ever been able to be produced on Earth. And therefore, the agreement between the black body prediction of quantum mechanics, and this is at the level of 10 to the minus 5, and therefore you can test quantum mechanics at that level. It's interesting. You can use quantum for those people who like to test quantum mechanics if they don't believe it. Okay, let me just show you the pictures and get this over with. Why does COBE provide you a picture of primordial density fluctuations? When we look out at the universe today, we see galaxies at a redshift of 2. What we're seeing when we see the microwave background is radiation emitted at a redshift of 1,000, because the universe became transparent to radiation at that point. When I look at that wall, I can see out to that wall because air is transparent. I can't see past the wall because the wall absorbs light. The universe is the same way. It's transparent until you go back in time until it becomes ionized, and then it absorbs it. So if you look out, you see the surface, where the universe stops becoming opaque, and that's the microwave background surface. Now, at that time, you can ask how big on that surface. You know how the radius of that surface. Okay? How big is CT, the time at which that took place? CT is about 2 degrees. Therefore, any structures larger than 2 degrees cannot have been created by causal physical processes since the FRW expansion began, and had to be primordial. And that's why this is so exciting, because here are the pictures that came from COBE. This is, I think, the 4-year data that I got from Juan here, but the 1 or 2 year data look the same. There are lumps. This is the galaxy. There are lumps. And the point is, the COBE beam, the COBE smoothing scale is 7 degrees. The pixel size is 2.5 degrees. So any structures that are seen here are in scales bigger than the horizon. And they're primordial. That's what's so exciting. What next? Well, you can look at that picture over a 2 pi or 4 pi surface, and you can do what any one physicist would like to do, which is decompose it in spherical harmonics. And then you can talk about correlations of temperature fluctuations in terms of the coefficients of these spherical harmonics. And the important thing to realize is that higher spherical harmonics mean more wiggles, and more wiggles means smaller wavelength. And smaller wavelengths means higher wave number. So there's a one-to-one correlation between the mode number of the spherical harmonic decomposition and the wave number. And therefore one can make predictions. And the predictions tell you that as you go to higher, COBE was able to measure up to L equal 10 or 20, because it measured up to 7 degrees and higher. If you want to get smaller scale, you're going to measure higher L modes. And for higher L modes, you're eventually going to measure modes that are actually inside the horizon at the time the microwave background was created. And then they can respond to physics. And so you can make predictions based on things, and you can ask how the spectrum would look like. And here's a well, actually let me actually present something with some axes. Well, here's one prediction. Axes. And what you find, here's where COBE measures the spectrum here, and you see all this stuff. All this stuff depends upon a lot of interesting physics and cosmology. And so what one would like to do, as I'll show you in a second, is be able to measure that stuff. To measure that stuff, you have to measure small angular scales. Well, there have been some experiments to measure small angular scales already from the Earth, and there are lots of them. Here's COBE. It measures large angular scales, small wave number. And there's a lot of experiments here. And what is intriguing, although dishonest, is to plot a picture like this, because it guides the eye and gives the illusion that somehow this data is agreeing with this picture, which it certainly isn't at any scale yet. What we'd like to do is actually get a picture where one can compare the predictions. And that's what COBRA, SAMBRA, and MAP are proposed to do. Here's the microwave background fluctuations that's seen by COBE. Here is what the next generation of all-sky satellite cosmic microwave background detectors are supposed to be able to do. And what does that mean? It means if I take the prediction, for example, that I gave you here. Yeah, I guess that's right. And I ask what the observational uncertainties will be. Actually, this is wrong. These grow here, but it doesn't matter. This is irrelevant. They are claimed to be this. Now, you see, that's quite interesting. Because where these bumps and wiggles, and I don't have time to describe them today, go from depend on an amazing number of things. They change depending upon whether you have lambda, or cold dark matter, or some hot dark matter, or cosmic strings. So if you could measure this, and also on the Hubble constant, if you could measure this to this accuracy, you would measure every major parameter in cosmology at maybe the 5 to 10% level. You would know H naught, lambda, omega baryon, everything. What does that promise us? Well, of course, what that promises us is the death of cosmology. Because what it threatens is to make cosmology as interesting experimentally as the standard model of elementary particle physics is today. Well, is that the future? I don't believe it's the future. Because I believe that experiments will always come to the rescue and muddy the water. Because what I showed you is a theorist's prediction, again, of what the detector will be able to do and what it will see. And I've never once in my life seen a theorist's prediction in advance of the kind of accuracy that has been proposed. And I'm convinced, at least I certainly hope, that there'll be the new data will actually muddy the water. So that, I believe, I hope is the future. And what are the major challenges that I presented to you? The age problem is an issue. The baryon problem is certainly an issue which has to be resolved. Large-scale structure problem is all of these. And all of these lead to a new minimal standard model. Not yet supersymmetric, but I'm sure it will be in time. In which perhaps omega in cold dark matter is much, much less than 1, which is very different than one would have said 10 years ago. And the way around that is either the total density is less than 1, or there's a cosmological constant, or something uglier, in my opinion, there's a neutrino with that kind of mass. And the millennium, many people always predict that the millennium brings doomsday, and potentially it does. Because the millennium, with the next generation of cosmic background detectors, puts us on the threshold of addressing all of these problems, which, as I say, is doomsday for any theorist. Okay? Thank you. Well, I went over time again. I think I'll take 2 or 3 questions if there are any in public, and then some private. For the moment, anyone other than Doug Morrison, and then if there's no one else, we'll have to take that question. I know, but just see if there's any other questions. No, chickens. Okay.
Well,
yes.
I don't quite agree with the solar neutrinos, but the solar neutrinos, whenever you look under the carpet, you find a pile of dirt. And for 6 years I've been saying, when you compare experiment and theory, you should not take the small error, you should take the small and the big error. And even in the figure you showed there, it's only the experimental error, even though the theoretical error is much bigger. For example, for the chlorine experiments, you quote 10% error, but the real theoretical error is about 30%. So if you take Dan and Shadi, which agrees exactly with Kemia Kandi, if you take Turkesi, it's about 1.9 standard deviations. Now, it's much more with McCall, because his error is not 30%, it's 15%, and his value is much higher than the other two. So there's a problem here.
Let me just, obviously it's not the place to have a protracted debate, and I don't think I even want to, but I've spent a lot of time looking at the models and actually working with them and analyzing the data. And I think the data is very suggestive that there is a problem. It's suggestive, it's not definitive. I agree with you with that statement. It's suggestive at this point, and it has been suggestive for 20 years, and my hope is that it won't be suggestive for another 20 years. But if you look at it, it is very difficult to adequately explain the data. Not impossible, but very difficult. And so I have a theorem that I try to live by, which is that I like to keep an open mind, but not so open that my brains fall out. And that's not from me, that's from the publisher of the New York Times in 1955. But in any case, it's not yet there. I would say that but the data is suggestive enough that I think it is, if I were going to bet, I would bet against an astrophysical solution. And I think I'd bet fairly strongly. I'd give very large odds, which is really the only way to do it. So the question is, if you want to bet $100,000, we can talk.
What odds are you giving?
Well, we'll talk. Depends on the money you want to bet. But I've discovered the only way to really see if people believe what they're saying is to ask them if they want to bet that kind of money. Well, I'll come back to you in a second. Yes?
I think you said that you really didn't depend synthesis to like neutrons and helium. Otherwise, we wouldn't be here. But in fact, okay, if you create absolutely no helium in Big Bang, what is so different? I mean, most of the elements, heavy elements, we debate in stars. So we won't see helium around in the sun, but so what? We believe with a purely hydrogen universe without anything.
That's actually an interesting question. No, I don't think so. I think because let me see. Yeah, no, it's an interesting question. I don't want to answer no yet. You might be right. I'd have to think about how efficiently the stars have created, of course, very little helium compared to the amount of helium there is around right now. But does that matter? I think it probably does. My bet is that, well, I don't know. You'd have to think about how much heavy elements would be produced by supernova if you didn't have that much helium in the first place and had to burn 75% more than you actually burn in stars. It's an interesting question. You're right. You caught me again. Well, I tell you what, I'm going to let people go and you can ask me the next question in private. How does that sound? Because it might be more embarrassing. Thank you very much for your patience. It's a good point.
It's much better than 10%.